Hey everyone, my name is Muhammad Faisal, and in this video for our broadcasting course, we are going to talk about antennas, radiated power. We'll go through the concept, the formulas, and I'll walk you through the few example step by step. So let's start the presentations. So before we dig in, here's a quick look about what we'll cover today. First, the basic antenna parameters, then the three core quantities like radiation power density, radiation intensity, and the total radiated power. So after that, we'll solve some example together, and finally, we'll talk about the directivity and gains, which are super relevant for our course like broadcasting. Okay, let's begin. So, all right. First thing first, what is an antenna? Okay, we simply put it takes a guided wave like signal traveling in a cable, and then turns it into a wave that radiates out into a free space. So in broadcasting, this is exactly what sends the signal out to your audience. Now, to describe how well an antenna radiates power, we use three main quantities in here, such as radiation power density, is like measured in watts per square meters, and then radiation intensity in watts per steradians, and the total radiated power in watts. These three are all connected, and we look each other one by one. So let's start with the first one. The first one is radiation power density. This is basically tell us how much power is flowing through each unit of the area. We get it from the time average Pauling factor out in the far field region. So like the formula you see here is 1/2 times the real part of E cross and H conjugate. And if we just want in terms of electricity field, it becomes the magnitude of the E squared over 2 eta, whereas eta its intrinsic impedance for the free space is about 377 ohms. Okay, so keep that number in mind before we next to this radiation intensity. This one is the power rated per unit solid angle. That's the steradians, and it's getting pretty easy. Like you don't just take another power density than from before and multiply by r squared. So here's the neat part. Once we do that, we distance drop out completely. So radiation intensity is only depends on the directions, right? The angles theta and the p, and down here is the solid state angle elements, such as like d omega, which is equal to sin theta, d theta, dp, and remember this little guy before because it shows up every single time we integrate. So move up to the total radiated power. So in this slide is really the heart of the everything we discussed about the total radiated power. This is all the power of the antenna senders every directions combined. So to find it, we integrate the radiation intensity U over here like this, U over the whole solid angle, like the full spare for P integrants. Now notice this sin theta over here is the inside the integral that comes from the solid angle element we just talked about. So don't forget it. And for a special case, an isotopic course that radiates equally in all directions, the average intensity is simply P rad over 4P over here. This is for isotopic source. And the total power channels in all directions, we can find it by integrating the radiation intensity over the entire sphere. So next up, we have the other key formula like such as directivity, gain, standard integral sin squared, and the standard integral sin over 3. So before we get to the example, here a few more keys formula you want to know. Like so here, example again is just the radiation efficiency times the directivity. Such as like in the bottom with the integral of sin squared theta gives p over 2, and the integral of sin cubed theta gives 4 over 3. So, okay, trust me, guys, you'll see these two a lot. Okay, so it's worth to memorizing them. So, let's begin on work example number one. So let's put this into practice with our first example, right? We're given the radiation power density A r hat times A naught sin theta over r squared, and we want to the total radiated power. So step one, we'll find the radiation intensity by multiplying the r squared, which is given the u equals uh, a naught sin theta. After that, we plug that into our total radiated power integral. Now, what's this? We got sin theta from u. I'm sorry, this is now what's sin theta from the solid angle. So together they makes sin squared theta. Okay. After integrating, we get p squared times a naught watts, and that's our answer. Okay, let's try the second example. This time the problem hands us the radiation intensity, directivity, the U equals the 5 sin theta over here. So we just plug it into straight into the integral and notice it's exact same pattern as before. We get sin squared theta, whose integral is p over 2, and the dp integral gives us 2p. So multiply it all out and we get 5p squared, which work out to about 49.35 watts. So this antenna radiates roughly around 49 watts in total. Move up to the example number three. So for the example here, which is the little difference, here intensity is the B naught sin squared theta. When we drop that into the integral and multiply by the sin theta from the solid angle, we now get the sin cube theta like over here. And this exactly where the second standard integral comes in handy. Before the integral of sin cube theta um, equals of the 4 over 3 work in through, and the total radiated power comes out to the 8p b naught over 3 watts. So here's the standard integral since 3 over 4 over 3 shows up. Okay, it's still number 3, but now the part B is to finding the maximum directivity. So the maximum value of u here is b naught, so which happens at theta equals 90 degrees. So we use our directivity formula instead of another directivity formula. For p u max over p rad, the b naught cancel out nicely here, and we're left with 3 over 2 or 1.5 like this, 4p b naught over 8p b naught per 3 equals, this is all missing. I mean disappear. This is just 3 over 2, so it's equal 1.5. And if we convert that to decibel, we can use the formula over here. As it 10 log of 1.5, we got around about 1.78 dB. So that number tells us how focused and how directional the antenna radiation is. Oh, I'm sorry. Uh, so So you might be wondering why those all these matter for broadcasting. Well, three big reasons. First, total radiated power determines your coverage. So how far you want to transmit signal can actually reach the audience. Second of all, the directivity lets you focus that power towards your surface area instead of wasting in every direction. That's the thing we don't want to do it. And third gain factor than efficiency and losses. So it tells you the real signal strength that reached the receiver. That's why these calculations really matters for anyone working in broadcasting. So, right, let's wrap it up. First, we find the antenna radiated power by integrating the radiation intensity over the entire solid angle, such as 4p radians. And then second of all, that sin theta factor always shows up, which is why the sin squared and sin cube integrals are so important. Third one, then once we have the total radiated power, we can find the antenna's directivity and gain. And finally, all of this together decide that coverage and the quality of the broadcast signal. Can it be? So, okay. And that's it for the video. Thank you so much for watching. I really hope this helped you understand antenna radiated power a bit better. So if you did, go ahead and try the example again of your own, or you can try it another source on the internet. All right. Thank you for watching. See you in Goodbye.